Yeah, I'll start my presentation. Hopefully, it will be visible to all of you. And if you cannot hear or see the presentation, please write on the Q&A. We should be able to see that and hopefully debug the problem. So today we are gonna talk about the title of the presentation is towards a safer subsea production system. So this will be in effect, it's a general idea of how you can use simulation to provide a solution for a complex system and very safety critical system such as subsea production. And for the particular example, we chose the some subsea jumper. So we'll look at a jumper design optimization. Of course, it's a very detailed problem. There are a lot of variabilities. For the current example, we'll take some of the variabilities, but also will present a general idea about how you can have a solution for the complete problem. And as for my background, I have a PhD in mechanical engineering from University of Iowa. I worked on fracture mechanics and probabilistic analysis, the optimization, and then I have industry background in nuclear as well as oil and gas. So I'm in Houston oil and gas industry for almost now 4.5 years. And as part of my engagement, I've been engaged with various ECA and fatigue analysis, strength analysis, optimization, and even I've done some plugin development and all. I'm moving to the next slide. So as an overview of our company, so Bias is, it started last year, so we are still a new company, but most of our people have years of industry experience when we do have people from different industry backgrounds, as well as we have our team, in our team, people who have worked in simulation companies such as Dassault System, which as you know are the provider of Abacus and other simulation-based softwares. Currently, we are based out of Houston. It's our main office is in the Energy Corridor. We also have satellite offices in other U.S. cities such as Cincinnati, San Francisco, and Detroit. And as I mentioned, we are solution partner with Dassault System Simulia. So we work with providing you the solution for Abacus, iSight, FESafe, and Tosca. And apart from that, we also do engineering consulting, software training, and also industry-based training, and we do provide hardware solution as well. Okay, moving to the next slide. So as our services, we provide customer-tailored software solutions with complete implementation. Through our consulting service, we provide clients their solution for their problems, including our talent pool from the global talent pool. We also have tie-up with testing facilities, and we also provide data analytics-based solution. We do provide training at our facility in Houston and also at other cities as and when needed. And the trainings can be customized towards your need. Now, starting with the discussion today. So as in general, of any subsea production, it's a very complicated system. There are risers and umbilicals and subsea equipment connectors, which is like jumper is an example. So it's a flexible connector between two rigid parts. And then also there is a pipeline system, and also these are all these face harsh external and internal conditions, as you can imagine, because it's in the sea environment, things are pretty rough. And also we need high safety and quality standards, which is of course mandatory. So detailed look into a component required to guarantee safety. So one needs to be very careful about designing a subsea equipment. So in this study, we are considering a jumper, so which basically can connect from the tree to the plemb. So here we'll look at the jumper optimization. Now, in general, for virtual product development process, so you go from physical to virtual prototyping. So you have the physical data, the loading condition, design constraint, and everything. So from there, you do a virtual prototyping, which is simulation based. Uh, by doing a virtual prototyping, we can deliver safe products. We can accelerate the development process because now you're running a simulation rather than doing actual testing. So it can be faster and efficient, and is improve the system reliability. So this is very important because there are a lot of variability, as we'll talk in a few seconds. Even in jumper design, there are a lot of things that can change. So using a simulation based approach, you can bring in all those scenarios and you can analyze the effect. It doesn't have to be a reliability analysis per se, but you can look at the design, you can explore the design, see what are the trends in that, or what are the so critical zones. And by using a reliable and robust design, we can of course increase the component durability. So we do all this thing, but at the same time we can reduce the maintenance cost, because if your design is pretty robust and reliable, and if you can anticipate the problems during operation, you design in a way that will reduce the maintenance cost. And all this can done by avoiding a lot of expensive testing. Of course, you have to finally do some testing to qualify the product, but it can greatly reduce your number of tests. Now, generally in a jumper design activities, we look at basically three first two things: strength and fatigue. And then depending on the fatigue life, we can also do a engineering critical assessment, which is basically fracture mechanics based fatigue and fracture analysis. So for the strength analysis, we'll look at the onshore and subsea hydrostatic testing mode. There are installation modes, and there is soft landing operation and non-operation mode, which includes tree workover. And also there can be accidental loading, which is the ROV can come and hit the jumper, the dropped object problem. So once we qualify the jumper for the strength design, then also we look into the fatigue part of it, where we look at cycles over the design life. Sources of fatigue can be operating cycles, VIV, FIV, or flow-induced pulsation. So in the current example, we are going to talk more about the flow-induced vibration part. But as I'm saying, it's a general problem, so you can use simulation to provide a complete solution. Now, if the fatigue life is excessively high, or if it doesn't pass the SN-based fatigue life, then one can always do the engineering critical assessment, where the initial defect is taken into consideration, and we can look into propagation and fracture. Now here, just to give an idea about the complexity of the problem. So as for parameters that comes into jumper design, this can be misalignments, thermal expansion, which can come because of your pipeline thermal expansion, which interacts with, again, the soil friction. There's material properties and all. So that gives a range of thermal expansion values. Then for the installation, there is always a target box, because everything is made based on the survey. But when you are doing an as-built, the actual scenario may be different than what you have anticipated for. So there is also always a variability. Now the flow line lay angle can also play a factor, because depending on how the flow line is laid with the jumper plane of the jumper, your thermal expansion effect that goes on the jumper can be different. And also the material property variation, internal flow property. So in the current analysis, we are looking at more on the internal flow. And also there are external flow properties, which is the current. Now on the picture on the right, so we are showing like a plum and a tree. So if you want to put a jumper, it can be, so one can consider a nominal case, but in reality, when you are trying to put the jumper, it can be as worse as case C or case B. So case B is like the longest length of the jumper, and case C is the most twisted. So the angle that it rotated, so which is the worst case scenario. So all this has to be considered in your jumper design, because you don't want to design a jumper for nominal values, and because of all this variability, in reality, it can be an unsafe design. And this makes the problem very complex. However, in the current, however, you can take all this complexity into account in your simulation. For the current purpose, it's more of an example. We are trying to show the value of simulation and how you can use that to model a jumper. We are only considering internal flow properties. Uh, so here is how simulation can power innovation. So we start with the product requirement. So the jumper can have certain requirements. So it has to meet this strength criteria, this fatigue criteria, and then you try to understand the physics. So for this example, we looked at the flow induced pulsation problem. So that considered to be an effect within the jumper, the significant effect in the jumper design. Now, different design alternatives were explored using a component of Simulia, which is eyesight, and then a optimized design has been achieved. Now, general optimized design of the jumper, once it is achieved, then we looked into the problem of where the jumper is coming to the connector, where we look at the stresses at the flange fillet. Idea is to optimize the shape of the flange fillet so that the high stresses are reduced there as much as possible, which of course has an effect on the durability. So with lower stresses, we'll have a more durable design. So this is the whole process that we are looking into. Now here, let's look at the different components that we used for this simulation. So first we looked at analyzing the existing design. So we always start with an existing design, right? So there is something to start with. And then we use that via fluid structure interaction using Abacus and star CCM. So in this case, Simulia component Abacus is used, and also star CCM is used for the flow simulation. And then once we have the basic input output, which is the pressure coming from the flow simulation, so eyesight is used to come up with the various test cases, which is used then in a design exploration case to reduce the deformation, bend stresses, and pressure loss of jumper via design of experiment analysis. So this is eyesight is another component of Simulia. And then, as I mentioned, so we looked into the flange fillet at the connector. So now Tosca structure, which is used for shape optimization, is used to minimize the peak stresses at flange fillet by changing the fillet shapes. And then finally, with the stresses from Tosca, we performed a durability analysis with FESA, which is generally used for metal fatigue analysis to check the lifespan of the new design. So this is in general the layout of the problem. Now again, so we have this circle for various steps. So starting from the product requirement, and also I'll get to the individual ones. So first you start with the product requirement, you come up with the initial design, and then start exploring that design with the variability that you have. So now next step, before you start modeling, you need to understand the physics in this problem. We looked into a flow induced vibration problem. So we considered an event where oil mass flow rate changes periodically for a given lifespan, so time span. Now it gives rise to a transient FSI simulation, which is done through star CCM. And we made the frequency of transient phenomenon equal to close to the natural frequency of the jumper. It may not be an actual case all the time, but this gives you a worst case scenario, and it shows the value of what we are doing, because it makes the jumper very critical because of this natural frequency due to flow, due to the flow change of flow during with time. Now we identified the deformation and stress distribution along the jumper wall via fluid structure interaction module, which is here we use the star CCM plus. Next step is to, once you set up the problem, now next step is to basically, now you know the parameters, so what you can change in your design, and then you vary the design parameters and look for a very good design that satisfies all your criteria. So here, which is basically reducing the pressure drop and decreasing the maximum stress in the jumper. So we looked at different design alternatives using eyesight. Now here it shows the design of experiment module within the eyesight. So it consists of 4 components. So it uses the abacus, which creates the subsea jumper geometry, FE mesh, and abacus input file. We have used Python scripting for that. Then star CCM is used to run the FSI problem, and then it creates a .odb file and calculates the total pressure loss. And then we used abacus post processing, which use the ODB file and identifies the peak stress values and the deformation. And then finally in the DOE model, which is basically changing your design variables and then get output for your every set of design variables. So suppose you have 10 different sets of design parameters, then you for each set you run this whole loop one time and get the output. So then you will have a input output values, set of input output values, from which you can look at, okay, changing what changes my design in which sense, and then you can choose that design parameter and modify that. So here we have used the Latin hierarchy with standard DOE technique, which is basically a smart sampling technique. So objective is to reduce the deformation, bend stresses, and pressure loss for subsea jumper by varying the design variables, which are the radius 1 to 3. So we made this problem symmetric because in reality, most of the time manufacturing is a big player, right? So from the manufacturing point of view, you don't want to have too much of variability in your design. So for the range, for the bottom radius, which is radius 3, you have the ranges from 0.3 to 0.2 meter, and for the top it's 0.3 to 1 meter. So within that range, so it's always, the range has to be always defined for the DOE study because it generates sample based on the range. So this is how we define the range in the particular problem. Now using the symmetry, we ran 21 cases, and as you can see on the right, so there are radius 1, radius 2, and radius 3, because 5, 6, and 4 are just say a symmetric value of the radius 1, 2, and 3. So we have all this 21 cases. We ran all the abacus, star CCM, all these components for each of these cases and get the output values of interest. Now, once we have done with the DOE, we have run all the cases in the DOE matrix. We look at the inspect the impact on the deformation and pressure loss. So we looked at the pressure loss and deformation. As you can see, the radius 2 has the maximum effect. So this is like a Pareto plot, and you can also do an approximation to see how the parameters are affecting your design. So we started with a design where all the radius are 0.5 meter, which is a reference design. So first design proposal, there are 2 design proposals we have came up with. One is all the radius will be made same, but then since the radius 2 was giving the maximum effect, we increased it to 1 meter. And of course it's understandable that as you are increasing the radius, your stresses as well as pressure drops are reducing. So we took the 1 meter, which is the maximum possible for the top radiuses, and assigned it to the radius number 2, and also made the condition that all the radiuses are of the same value. That's why from radius 1 to 6 we have all 1 meter. And in the next proposal, so what we did, again, it's the radius 2 is the most critical design parameter, so we assign the maximum value possible, so 1 meter. And also we made the design symmetric, so we made the radius 1 and 3 same as the reference design. So we only changed the radius number 2, and because of symmetry, radius 2 and 5 are 1 meter, and all the other radiuses are 0.5 meter. So we have these 2 different design alternatives, and we studied the effect of those designs. So using the proposal 1, where all the radiuses are 1 meter, we saw a 22% reduction in the maximum displacement, 15% reduction for fluid pressure loss. And for the design proposal 2, where we only changed the radius 2 and 4, and all the other radius are kept as the initial design, we saw a 17% difference reduction in the max displacement and 5% reduction for the fluid pressure loss. So you can see both achieved to some extent the target that you are trying to get there, but this is again an example case, but here it shows the proposal 1 probably gives slightly better value compared to your proposal 2. Now, coming from the now after we optimize the pressure loss and the deformation, we looked into the we looked at maximum peak stresses at the flange fillet. The idea is to reduce that peak stress. So for this one, we created a sub model, including the flange section with bolts and the jumper end, and use the deformation. We have used the deformation data of the global model as boundary condition for the sub model. In this particular case, we considered both the all design alternatives, and we looked at what is the effect on that. And now we ran the Tosca structural shape optimization starting from the maximum fillet radius. That's kind of part of the initial design. And then the objective is to maximize the minimize the maximum one miss stress. So basically minimize the stress field at the junction fillet radius. So the optimization using Tosca was completed in 15 iteration. Again, this is an example. It can be done in, I mean, depending on your other cases, it can be 10 or 20, but the idea is to within a not too many iterations, you should be able to come up with the optimized design. This led to a peak stress reduction of 30% compared to the reference design with circular fillet. Now, coming from the Tosca analysis where we reduced the maximum stress, we came to the durability analysis where we are going to use the stress values, and we looked at both the jumper, general jumper shape, as well as their connector, as well as the connection point to look into the lifespan. Now, for FE safe analysis, which is used for metal fatigue assessment, so we use that one. We have to quantify the impact on the lifespan for given oscillation event. So here is the on the right, you can see the input signal that's going to be imposed on the jumper, and that will be called. So every certain repetition of that. So FE safe will calculate how many repetition of that input signal you can afford before it starts having damage, which is like having a critical flaw. I mean, having a dominant flaw size is like end of your fatigue life. So that's where you are looking into. So this analysis is undertaken for a global jumper model as well as the sub model. FE safe analysis quantified the impact of the oscillation on the lifespan, and it looks at the all nodes. So there you don't have to select a particular region. If it is a very complex problem, yes, you from your experience you can select certain region, but this is not too many nodes out there for this problem. So we selected the entire domain for FE safe to look into the fatigue life. Now, what we found out that we all with from the initial design to the optimized design, and these results are pertaining to option 2. So option 1 we had, sorry, this is for option 1, and option 2 also we have similar results. So almost 40 times longer lifespan was obtained using optimized design. And this doesn't use any code factor, and also it's just a total number of repetition of the cycle where you can get your fatigue life, so without any factor being added. So if you add the factor, it will be added to both the cases, and the life ratio of the life for initial and optimized design will be the same. Here for the fillet, we saw from the initial design to the optimized design, there is a 60% longer lifespan. Again, this is because the fillet shape has been optimized and the stresses, maximum stresses has been reduced, and that affects the fatigue life that you can afford. So it does improve the durability of your structure. And in this particular case, just want to mention that, I mean, durability can be of a very big concern, because if you have an initial crack that that can grow and start to fail, then it can be a catastrophic problem. So another thing is, if you do a fatigue analysis, that's the first cut analysis. If you find there is a problem with the fatigue life, you can always do a engineering critical assessment, so which is a fracture mechanics based fatigue and fracture assessment. You can assume the initial flaw size, and most of the time it depends on the non-destructive testing that you are doing. So what is the sensitivity of that testing? So any crack that you cannot detect, you will assume that's the initial shape of the crack, and then do a fracture mechanics analysis. Now here what we have achieved, so we came up with a jumper requirement. We had an initial design, we did design exploration and come up with two optimized designs, and we looked at both of them. And using Tosca, we increased the lifespan at the fillet, as well as at the fillet radius, and as well as the jumper in general. And FESafe has been used to do the fatigue calculation. And once you have a design like this, one can always go and do testing and validate the new design and sign up for installation in the field. Of course, this particular problem does not capture all the aspects of the design. As I mentioned before, it can be a very complex problem with a lot of variability. But I hope it does show that you can always increase the detail in the problem, but with this process, with this flow, you can always achieve your optimized design with all the complexity that the problem involves. So in a summary, what it shows here is the optimized design significantly reduce the deformation and bend stresses, and also at the fillet stress, and increase the lifespan for the jumper, bend, and fillet areas. Now, as you can see from these videos here, within the optimized design and initial design, so the optimized design on the left is, if you look at the oscillation, the box we are showing there, so it is less than what your initial design is. And again, this is an example problem. What it shows that if there is a problem with simulation, you can detect that problem and come up with a design that work against that, so that minimizes that effect. So you can have a more safe and durable design at the end. Finally, the value proposition. So we can use a realistic simulation for general subsea system. So it can reduce the cost of downtime because of any failure and any effect in the life, even the maintenance, and of course the development, because in the development cycle you are using simulation, you are not using actual testing but virtual testing, which significantly uses your time and cost for the development. And also you will have initially a lot of variability, so you can consider all those variability, so a last minute design change can be easily incorporated into your final design. And then also the engineering resources, as I'll show you in a minute. So this is where the resources part comes in. You can basically automate all the process. I mean, most of the process, if not all, and then that can significantly reduce the resources you need, especially in the crunch time. And also any changes that you want to make to your model can be easily incorporated, because everything is automated, and if there is a change, so the change will automatically be incorporated into the model. So here we have worked on some jumper design automation. Again, this is a work in progress, and it had a particular purpose, so it doesn't capture everything, but hope it will show you a very good idea of how you can automate a complex design process such as a jumper. So we considered here planar and non-planar jumpers with U, M, and Z shape, and also, I mean, you can extend it to any arbitrary shape if there is. I mean, normally most of the jumper will be M or U. Also, there are options for bend and sharp corners, so you can choose the pipe or elbow element, thick or thin wall formulation. So all these variabilities, all these different factors that you have to consider in the design, maybe coming from manufacturing or some other requirements. So you can use bend, sharp corners, different elements. So you have all these options, and nobody actually has to go there and do all this detailed modeling. You just choose the option, and then it will do the work for you. So the loads it considers is pressure and point load, and any other load, if that's known there, you can include that. Boundary condition involved thermal expansion, misalignment, rotation, settlement at the ends, work over deflection. So all this can be included in the boundary conditions. So analysis condition, we looked into hydrostatic test, operation with corroded wall thickness at 100% of life. That's a conservative assumption. So even at the end of the life, your structure should be safe. Workover and operational fatigue, because fatigue goes to the entire life of the jumper. So we have taken corroded wall thickness at 50% of life. And we also looked at the natural frequency. So we look at the stress and natural frequency. The ECA part is not involved in this one, but one can easily incorporate that as well. So it can be a condition, or unconditionally you can do an ECA independent of your fatigue level. Now I'll briefly show that there is a, so this is the jumper automation tool. So this is a video screen capture video we have. So it basically it works right now as a plugin inside Abacus environment, but again it's a generic graphical user interface which can be made for any software. So initially we create a working directory just to make sure all your files are saved, project files are saved in a directory that you want. And then you start creating the model. So it gives you an option for project description where you put all the details of the project. And this will be stored in your output file. So anybody bring that file will see which project and what details are there. So these are the different options. So you can choose from elbow and bend, outer diameter, and this all this figure says what is A and B. So yeah, now going to the jumper geometry and load. So you can type all the values in here, or you can go and read from a file. Generally, it comes from a different Excel spreadsheet, which somebody probably have worked on based on certain considerations. So you upload that CSV file, and it gives you all your geometry details, as well as the loading. So these are more on the material characteristics, densities that we are going to use, and also the operating condition, pressure and temperature. Again, all these parameters can actually be read from a file. So you can create an input file where you can just upload the input file, and it will, all these boxes will be automatically populated, and which also gives you the batch run capability. So here different boundary condition and meshing is given, and it also says what element type you're going to use, what's the wall formulation, is a thick or thin formulation, and also we'll say the number of eigenmodes for your frequency analysis. So once you hit the run analysis, of course it has some warning message and everything that pops up. If you want, you can put them in a file as well. So later on you can take a look if something goes wrong, where it goes wrong and why. The actual modeling and everything is going on in the Abacus. So it's on the background, so everything is going on there. So it's all automated. It's running the kernel script in Abacus. Yeah, so it's completed the input file processor, and now it's going to do the analysis. And of course, as you can see, it's a very quick analysis. Yeah, so it's running the different cases. So every file doesn't take long. And it is also not doing, there is no like 3D elements, and also the geometry is only non-planar. So here we are showing, so once that you can always go back and check all the boundary conditions and everything. I mean, it's not needed. We just showed that if you want to do a debugging, or for the first time you are learning the problem, it might be a good idea to check all those. So now, since we defined the working directory, we know where all the files are. And then this is the output. As you can see there, says that it defines the software and everything, and then it also types in the project name, so you will know what project it is, who has run it, and everything, all the information. And then these are the results for hydrostatic test condition. It looks at the maximum stresses, and then it also does the code check with B31.8, and then another condition operating. So it looks at the maximum stresses and does the code check, and if it, I mean, you can see that it says fail and all this. So I mean, this is the arbitrary problem. So we just chose some numbers, of course. So it will tell you whether something is failing or passing. And then finally, it has the natural frequencies, which can be used later on for the VI, VFIB analysis. Yeah, so that's kind of a brief demonstration of the software. So similar automation tool can be developed, and depending on the particular problem or what parameters you have, what sensitivity required and all this, you can always put that in the automation script. So just that's kind of ends my presentation. This slide is just to tell that we are a certified Simulia support and training facility. We do provide engineering consulting and automation. You can email me at my email address at Vascorp, or we have a direct phone number. Also, Ali has, I think you have provided your email. So you can contact us by any way you want to work. So we have also on the website, we have a form. You can fill out that form and contact us. That concludes my presentation. So I would, if you have any question, please let me know. Can you help with that? So we have opened, okay, give me a second. It says Q&A is active in another session. Sorry, this is always the most difficult part of the presentation. Suddenly it says you are logged in from another computer. Okay, so one question here is, does FE-safe can be used with the FEA model using beam or pipe element? So as long as the stress results are there, as long as you have the stress conditions, stress values for different condition, it should be able to. So in the extraction part, you may have to do certain things differently, but as long as you have the stress values, yes. No problem. So if you have any question, I mean, you can always, we can try to unmute you, and you can always ask the question as well. So we can see here, right? Yeah, there is a raise hand option. Okay, I have another question. What stresses are considered for elbow elements? So we considered the maximum stress and one misses for this particular case. So max principal and the one misses. Damping factor used for the jumper. I need to check the value for that, but I can get back to you. But again, I mean, this may not be a realistic number because we wanted to have like less damping effect. So, but I'll get back to you then. Uh, do you have any question like on the process or how you can see a value of doing your jumper analysis or any? I mean, it doesn't have to be a question. Any comment is also very welcome. Yeah, please let us know. We are still here. So I'm guessing there is no further question. I mean, if you have any question later, or if you want to discuss about the problem that we solved or general process that we showed for simulation based design, please feel free to get back to us. You can call or email us anytime, or use our website to send in your queries. We'll be more than happy to get back to you and discuss in more details. And also, we are located in Houston, close to Barker, Cypress, and I-10 for those who are in Houston. So you can come to our office at any time. Generally, for first Friday of every month, we have a open house time where we would like to invite people who, with any question, can come to us and discuss about it, and we can like try to open the abacus and show you how certain things can be solved and all. So you are most welcome to attend that as well. With that, I would like to conclude today's webinar. Again, please feel free to get back to us if you have any question, and thank you all for attending and spending your time listening to our presentation. Thanks a lot. Bye.